So insertion sort takes an unsorted array and sorts it. And the way it does it is it ignores the first element and considers first the second element. It checks if the second element is less than the first element, and if it is, it swaps the two. So we get this. Then it compares the next element over, the third element, with the second element. It's less than the second element, so then it checks the first element. It's less than the first element, so it swaps. It puts the 2 in the place of the 3, and it moves the 3 and the 4 over, right? Because there's nothing left to compare it to. So then once that's done, it takes the fourth element and goes through that same process, right? Checks if it's less than 4. It is not, so it stays in the same place. Then it comes over here, checks the 12 with the 10. It is not lower than the 10, so it stays in the same place, and it continues doing that as we move our way down, right? We come over here, it compares the 1 with the 12. It's less than the 12, so it compares the 1 and the 10, less than the 10, compares the 1 and the 4, less than the 4, compares the 1 and the 3, then it compares the 1 and the 2. That's the last element, so there's no need to continue checking, and it places the 1 in the first element in the array, and it moves everything to the right, and that's kind of how insertion sort works. And one thing you want to notice is the left side of the array is a sorted list, right? And then the right side is the unsorted list with the element that you're considering right in the middle. And so this is insertion sort. It's code or pseudocode is right here, right? Notice that you're going to need a loop, and inside of the loop you're going to need another loop, right? Why? Well, the first loop is going to scroll through every number in the array, right? So 0, 1, 2, 3, 4, 5, 6, 7 to take a look at which element you're considering. And then once you have the element that you're considering inside of the loop, you need to have another loop, which is going to then compare this element with every element before it, right? Or possibly every element before it to see if it's lower. So you're going to have a nested loop situation, a loop within a loop. And when you have nested loops, the time complexity is n times n, with n meaning you need, if there's a list of n elements, you need to have n calculations in order to take care of the first loop, and then you need to have n calculations in order to evaluate the nested loop. So it's going to be n times n. It's n squared is the time complexity, which is not something that's gone over on the AP exam, but if you do decide to continue studying computer science, then that will become something that will become of interest to you, or at least will become of interest to the professor who will be giving you your grade. And n squared is not a good time complexity. Okay, so insertion sort, not very efficient. The next sort is similar. It's called selection sort. Right here, selection sort. And what it does is right here. So finds the smallest in the array, starting with the left side, and it swaps it with the unsorted sublist. So what does that mean? Actually, before we do that, we could see insertion sort in this animated GIF. So it doesn't compare to 6. There's nothing to compare to. It compares to 5 with the 6, less than, so it swaps the 2. Then it goes and compares the 3 with the 6, less than the 6. Checks the 5, less than the 5, swaps because it's the last or the first element in the array. Then it compares the 1 with the 6, the 5, the 3, swaps. And then the 8 compares it with the 6. Then nothing to swap here. We got the 7, compares the 7 with the 8, less than, and compares the 7 with the 6, not less than. So then it inserts it right in there, right? And yeah, it's going to go ahead and do that same calculation as we move our way down. So that's insertion sort. And then here's selection sort, and here's like a graphical representation of it. You have all of these different numbers. What it's doing is it considers all of these numbers out here, all these unsorted data points, and it finds the smallest value, right? So it finds the minimum of all of those, and once it does, then it swaps that minimum with the first element. Okay, then it considers all of the rest of the unsorted data points, finds the minimum again, and then it swaps it with the second element. Then it looks in all the elements and looks for the next minimum, and then it swaps it with the third element in the array, right? So that's selection sort. It's very similar to insertion sort, but there are some differences, and here's like a visual representation of it. Let's go ahead and take a look. Okay, so it's going to start over right here. It looks for the lowest one, the 0, right? And the red is the current minimum, right? So 9 is the current, then 5, then 4 is the current minimum. This is going a little fast, but what it does is it looks for the minimum in the unsorted array. You see the red is like the current minimum. Once it finds the minimum, it swaps it with the first element. Then it looks through the rest of the array and looks for the next minimum, and it swaps it with the second element, and so on as we work our way down. And if you continue that process, in the end you'll have a sorted array. Okay, so to execute this or to implement it, again, you would need a nested for loop, right? One for loop to find the minimum, and then the next for loop to insert it into the array. So this here also has the time complexity of n times n, right, which is not good. And let's see, is there an implementation here? Okay, so here is an implementation. We have a for loop going through the array, right? And then inside of that for loop, we are looking for the minimum with another for loop. So we have a nested for loop situation. Here's n, and then here's times n, right? So n times n is the time complexity. And okay, here's another implementation if you want to go and take a look at it. But I'm sure if you are tasked to do this, you can go ahead and code this yourself. And then last thing I want to end with is here is a note the URL if you want to take a look, is a cool little application where we have these different sorting algorithms. We have insertion, selection, bubble, shell, merge, heap, quick, and so on. And we have different sets of data points, right? One where they're all random, one where they're nearly sorted, one where they're reversed, meaning you have like the highest number in the front, the lowest number in the back, and then one where there are only a few unique data points, right? So you have like a set of 1s, a set of 3s, a set of 5s, and a set of 7s, right, that you need to sort. And if you go ahead and hit play, then it shows you how each of these perform against each other, right? And so you'll notice that insertion and selection both have a n times n time complexity, which is not good, n squared. So they lag behind the other implementations, which use like kind of innovative ways to get this going, right? Insertion and selection are searching algorithms that you would probably implement if you were asked to, right? Without having thought about it, like the first draft of a sorting algorithm, that would you'd probably end up with either insertion sort or selection sort. And then if you give it more thought and you kind of get more sophisticated, you move on down the list here, right? And each of these guys over here have more complex algorithms and they work faster, especially with large data sets. And the good thing is that we don't need to know any of these, we don't need to know most of these. We only need to know about merge, and we just need to know generally how merge works, not the exact details. And I'll go over that in another video. But insertion and selection, you need to know their inner workings fairly intimately, right? You need to know the difference. Just basically know the algorithm. And you also want to notice here that selection is slower than insertion on all the different types of data sets,